today, so I will introduce myself. Again, Dick Wilkins from Phoenix Technologies, and I'm going to talk about securing SMM. I'm going to do a general introduction, talk about the attack vectors on SMM, some mitigation strategies, and some things we've been working on for NX protection, no execute protection, and generally closed down. As you may have been aware, SMM, System Management Mode, is under attack. Our friends that formerly at MITRE were actively probing to see if they could find vulnerabilities, and in fact they did. They found a number of them. There have been a number of press articles. These are headlines that have been pulled from various places. How many BIOSes would you like to affect? We can brick all sorts of machines. They find vulnerabilities all over the place with here. And we believe at Phoenix that it's critically important that we as an organization address these things, and we'd like to help out. Specifically, we believe these vulnerabilities continue to be widespread. Many folks have come out and said, oh, we're not vulnerable. That seems to be a blanket statement for many companies, is to just, if they're not provably vulnerable, then we're not. In that way, customers and clients and that kind of thing, that's their corporate statement, is they're not vulnerable. We at Phoenix don't believe it, because we believed we weren't very vulnerable, and we found that we were. So we suspect that there are others that are probably in the same position we're in. They may, in fact, not be aware of it. They may honestly believe they're not vulnerable. But we suspect that that may not be the case. And we've developed some best practices that we want to share with you, and some potential code that can use to detect vulnerabilities in this space. And we believe that it's the right thing to do, to share it with everybody rather than keeping it proprietary. Of course, we had the corporate discussion about, should we patent this? This is a neat, clever idea. Should we develop a patent on it and try and collect royalties? And we decided, no, this is a security thing. That's not the right thing to do. We should make it widely available. So we'll talk about that in a minute. So here's some of the attack vectors. These are not super secret. We're not disclosing anything that isn't out there in the wilds already, but just as a reminder to you folks, most of you may be aware of these if you have any interest in this area at all. If you haven't cared about this, it might be interesting to you just in general. But one thing you can do is corrupt the content of SMRAM, the memory that's maintained in the SMM environment. Pass a buffer pointer right below SMRAM that has a size that's big enough to get into there and overwrite it. You can just end up corrupting data, and you can brick a machine quite easily this way. Various modifying pointers that shouldn't be in SMRAM to point to SMRAM, that kind of thing. There are many ways to cause this to happen. You can disclose the SMRAM contents. You can put a buffer pointer just outside of SMRAM and cause a valid routine doing the thing it thinks it's supposed to do, to copy contents of SMRAM out to unprotected memory and make it available for other people to take a look at. So if hackers are trying to figure out what things do and how to get access to them and where vulnerabilities might be, there's ways you can just essentially copy the entire contents of SMRAM out to places where it's accessible at runtime and take a look at it. Disassemble the code, whatever you need to do. So this is a potential vulnerability to just see what's going on. And arbitrary code execution. This is, of course, the nasty one that can happen anywhere, because SMI handlers, somebody said in one of the presentations yesterday that the firmware forms the root of trust for the entire system. Well, gee, SMM and SMI handlers are the root of trust for the firmware, essentially. This is where it all starts. So if you can execute arbitrary code in this space, you're in trouble. So if you can modify a function pointer that's outside of SMRAM to point somewhere into SMRAM and cause it to execute things it shouldn't, then you can cause this to happen. Also, there's an obscure note, we were talking about it yesterday, in some of the Intel documents, I believe, that say, SMI handlers that are no longer needed after boot should be deregistered after they're needed before OS present runtime, so they can't be exploited after the fact. A lot of folks are not doing that. They have SMI handlers all over that are part of the boot process, and they just leave them when they're done, and they're still there, registered, and could be used. So, and could be exploited, could be hacked in various ways. So, bad thing. Don't do that. Let's see. And one of the popular ones that's been out there is S3 boot script corruption, modifying either settings stored outside of SMRAM that end up disabling things in SMRAM, and using opcodes that are in tables outside of SMRAM to execute code in unexpected ways. Let's just put it that way. I don't want to go into this is not a detailed discussion of exploits here. That's not the point. But there are many ways to exploit things. So, how do we mitigate this? Intel provides this neat tool called ChipSec. There are several versions available for different audiences. Anybody who's writing BIOS type code, or I should say UEFI firmware, we should all stop calling it BIOS, by the way. Yes? Okay. But it's no longer BIOS, it's UEFI firmware. But anyway, this tool will do many things, including, I'm not going to read through the entire list here. You can read this as well as I can. But it verifies basically, is the chipset and the environment set up correctly? Do you have all the bits set that Intel believes that you need to have set for a running system? Is it configured correctly? And it's also extensible with additional Python scripts. So if you find problems or vulnerabilities are exposed, it can be extended yourself, and you can submit it back to Intel. I'm sure they'd be happy to accept your extensions in this to make it more robust and test more things. There's a new ChipSec SMI handler routine that allows checking of pointer vulnerabilities in SMRAM access, essentially, and it allows writing of test patterns into places and detecting if pointers are being used incorrectly. In this particular case, this may generate some false positives, but it generates an indication that code is doing some things that might be risky, and it probably needs manual code review if you detect the kind of thing, this kind of access. It's not necessarily wrong, but it might be. So it's a good way to check to see what areas you need to spend some extra time analyzing. It verifies that proper range checking is done and that kind of thing. So, one really nice feature that Intel's put in Haswell and beyond is something called the SMM code access check bit. And if you enable this, then running code from outside of SMM in SMM mode is a no-no, and you'll get a machine check exception. That's a really good test, but it's only available on Haswell and later processors. So we've got a lot of machines, a lot of processors that are still shipping and will be for a while that don't have this capability. So we want to talk about some, how can we provide this sort of protection when we don't have it in hardware? And I'm going to talk about that in a couple minutes. So additional mitigation strategies. We should turn on this code access check bit. We should enable this early in the development cycle to detect things rather than waiting to a final QA pass or something like this to try and detect this. There should be a routine part of the development cycle is to make sure this bit is on so you can detect these things early on and fix them. We Phoenix, believe that this needs to be enabled on all shipping platforms. We get pushback from some of our clients and customers saying, well, gee, if you enable this and it hits one of these, then essentially the machine won't boot, and we've got an angry customer. The thing is if you ship and it hits one of these, you've also got a fairly serious vulnerability in your SMM code, and you probably want to know that. Hopefully you will have gotten all these out of your code before you ship it. But if somehow some code that was vulnerable got inserted, gee, you'd probably like to know that. And this would allow you to detect that case. So you should be running the chipsec tool as routine part of your development lifecycle. You should turn on the code access check feature, or something I'm going to talk about as an alternative to that, and run through typical user scenarios just to make sure that everything seems to work. That's should be part of your routine QA cycle. So the question here is, can we rely on these tools to detect, the check bits and the chip check tool? Does this provide all the protection we need? And the answer is no. Tools don't support all types of silicon, all chips from all vendors, etc. They can't test all the use cases out there. There's going to be corner cases that are not obvious. And it's annoying to a company like Phoenix, and I'm sure inside and AMI. Okay. Gone right out of my head. To us, and probably for captive BIOS companies or firmware OEMs that have their own teams and ship firmware to different parts of their organization, they're in the same boat. It's annoying that after you've done all your work and all your QA, the customer or client or whoever you want to do turns on features you didn't think they were going to turn on. They change things, they can reconfigure it, and now we've got a configuration that wasn't thoroughly tested. Or they may just out and out replace code of yours with their own, or add SMI handlers that they want for super sneaky features. I know I've written a few of those in my time that have gotten inserted after the fact, I'm sure. So it's really good to turn on all the hardware features, but it's not a complete solution. So we've got to do code reviews. I'm sorry, it's painful, but SMI's, that SMM code is relatively isolated and smaller than the entire BIOS, and it's worth the time and effort to do proper code reviews. So here's a quick example code review checklist that we've put together. Validating all external data against buffer overruns, integer overflows, those kinds of things. Not exposing APIs and features not needed at runtime. Turn them off if you don't need them, deregister them. You must handle all errors. Asserts are not acceptable. The OS people learned this a while back, that you can't have panics and asserts all over your code, because either the asserts go away in a release code, and panics and things like that, if they're still there, they just cause the system to crash, and that's not happy customer. A happy customer is not going to accept blue screens or crashes. That's just, you shouldn't be sprinkling that kind of debug code in your production code. Should never call out of SMRAM, never call through function pointers stored outside of SMRAM. Don't allow external pointers to modify or disclose the contents of SMRAM. structures contain variable lengths or object counts, they must validate that they're reasonable and within the ranges appropriately. If you're going to organize a code review, figure out the list of what you need to look at, create a list like we were talking about a minute ago, and also code patterns of bad behavior, things like looking indirectly through tables to get to function pointers from SMRAM code that you shouldn't be doing. As you discover new bad behaviors, fix them and then list them, put them on your list of patterns to check in future code reviews. Think about implementing a default centralized range check function that everybody uses and provide that as an available feature for everybody to use rather than having everybody doing their own range checks and screwing it up. And again, pay really special attention to SMI handlers that get external input. What we did is we performed code reviews on all of the SMI handlers. We reviewed all the disclosures out there from the hacker world and through the various security response teams and that kind of thing to make sure that we were not vulnerable to any of those. When we found something and when we fixed it, we make sure that we backported it to any place that was possible and reasonable. Working with the customers. In our case, dealing with OEMs and ODMs, their focus is on getting products out the door. They want to make money. And so talking about security is sort of antithetical to them shipping products. And so you have to educate them on how important it is. I did a little talk in this session last year where I described the CEO in a court being sued for not paying attention to security issues in the code that his company delivered. And I just hate to think that of a major executive or CEO of a company having to explain why they left gaping security holes out in their systems. Use tools, and we developed a ongoing review process and strategy to make sure that we avoided inserting new bugs if we could possibly do that. So, the Haswell and later have the check bit. A lot of systems, all the systems before that, other silicon may not. We wanted to have that kind of capability. So we looked at tried to figure out a way to add that capability on hardware where the check bit wasn't present. I guess 3 years ago now, we announced at the Plugfest here in Seattle that we had developed some code to enable no execute protections in UEFI. So you could specify buffers and the data memory generally and that kind of thing as no execute. Getting some of the protections that OSs have had forever down into the UEFI space. The modern CPUs have a no execute bit. You just have to essentially enable page tables and set the no execute bit in the right places, and it just works. You take a page fault essentially, and you can detect that as an exception. I won't go through all the detail. I know this is a bit of an eye chart, but feel free when these are posted up online to spend some time looking at this. Turns out that this can be done selectively for SMRAM and SMM accesses and make sure that the right things happen. So this is, again, a bit of an eye chart, but it says the detail of essentially setting the no execute bit in the IA32 ER register and an x64 target setting the long mode enable bit in the same register, et cetera. And in IA32, you have to actually build page tables, but not a huge deal, and there's example code out there for that. In x64, they're already present. So we added functions to read the attributes for PTEs and did page table management. We added an SMM driver that uses our page table library to read the attributes, and et cetera. What this is doing is it's leveraging the stuff we submitted to Tiano Core 3 years ago. That enables no execute throughout UEFI firmware. And I'm happy to say that we're finally really close to actually having that checked into the Tiano Core tree and made available to everybody. We released it a while back, but there were a few niggly implementation issues between the maintainers of the Tiano Core tree and our stuff, and those had to be worked out, and they ended up making a few spec changes, a couple of, like 2 minor spec changes in the 2.5 UEFI spec that enabled them to go ahead and do that. So that code should be checked in shortly. So everybody can look at it and leverage that code. And what we did is we just leveraged that code in a special way to enable this in SMM checking. So basically, on every SMI, page tables are selected, paging and AX support is enabled, the original state is saved and can be restored on exit. They're configured with the XD bit. If improper access is done, you get a page fault. You get a machine check exception in the Haswell version. In this version, you get a page fault exception. Easy to detect. So what did we do? We enabled these protections, and we immediately exposed vulnerable drivers, vulnerable code in there that had this problem. We didn't think there was any, but there was. What we did made it really easy. We just used our debugging tools and set a breakpoint in the page fault exception handler. And when we hit one of these, you just look at the stack trace and, yep, there it is. there's the evil person that's done this. Really trivial to find out. In a matter of a few hours at most, you can find all the bad code that's going to do this. It's trivial to turn on. So you don't have to have the Haswell bit built in. You can just do it this way, and it works just fine. And we've done it on machines that do have the Haswell bit. Of course, we've chosen to do this as well, and it works just as well on the modern machines, the latest machines anyway. So this is critically important. These vulnerabilities are being abused out there. Some by government agencies, some, we hear all the horror stories out there of things going on and machines being bricked in disastrous cases. And we know that these kinds of things are happening. So we need to protect ourselves and do the right thing. So everybody should be doing these things. You must run all of the available tools. Make sure that if you've got the Haswell type environment, enable that bit. It's crazy to leave it off. You want to detect these anywhere in the development cycle, and it should be on in shipping systems. You don't want to have somebody insert some code that somehow starts violating this and adds a vulnerability, either deliberately or accidentally. All SMI handlers need to be analyzed, both tools and code review. And this doesn't close the door on all the traditional things about unauthorized writes to flash, capsule updates, roll back to previous version protection, those kinds of things. All those things, those also can compromise your SMM code. So you have to watch all those other things as well. We're just talking about a particular set of them here. And there are many attack vectors. Code developers need to adopt the following best practices. And you need to educate everybody who writes SMI code, any SMM code at all, You need to educate them about these things, because, and some of them are your employees, but many times they're your customers. So you need to educate them, because they're going to be inserting code after the fact and could open the barn door after you closed it and bolted it shut. They can open a window or whatever. So everybody writing SMM code needs to think, how can this be exploited? How could I use this to get in where I shouldn't be? Every bit of existing code must be reviewed. It's not reviewing millions and millions of lines of code. It's more a tractable problem than that. Any new code needs to be peer reviewed. You need a pair programming type process of some sort where every bit of code is peer reviewed, and an SMM code review must be part of your ongoing development process. You just have to make it part of your QA to routinely check back on SMM code, because it's so dangerous to get wrong. I remember, again, about 3 years ago, maybe it was last year, I don't remember, probably 3 years ago, Tony Magnifeste stood up here in one of his presentations and said, "We want SMM to go away." And by the way, this isn't the Microsoft view, and I didn't say that, but we want SMM to go away. It's too dangerous. And of course, everybody pushed back on that, and that's not going to happen. So SMM is here to stay for the foreseeable future, and it's a huge, dangerous hole. So you must take care of these, take these kinds of practices to make sure that it doesn't get exploited. That's it. You can look at CanSec West and Black Hat from the last few sessions to find more about the vulnerabilities and things like that. Questions?